All right, good evening, everyone. My name is Raghu, and I'll be hosting tonight's Balliol Online Lecture, the last one of 2023. And we're really lucky to have Dorian Gangloff, Associate Professor in the Department of Engineering Science, and also a tutorial fellow here at the college. So Dorian completed a bachelor's in engineering physics in British Columbia before pursuing a PhD in Vladan and Vulicic's group at MIT. There, amongst other things, he was studying models of friction using a single trapped ion in an optical lattice. He then moved to Cambridge, where he was awarded a junior research fellowship to work on quantum technologies and solid-state platforms in Meta Atatürk's group, specifically coupling a single electron to an ensemble of nuclear spins to a quantum dot. He was awarded a Royal Society Research Fellowship to start his own group in Oxford, which he will be unfortunately bringing with him to the new Cavendish laboratory in Cambridge next year. So just before Dorian starts, a reminder that if you have any questions, you can just put them in the Q&A and I'll be reading them out at the end of the chat. So without any further ado, Dorian, please.
Thanks a lot, Raghu, and good evening, everybody. Great pleasure to be giving this lecture tonight to our alumni and our community of Balliol members. I'll be talking to you about my field of research, obviously, quantum computing, but more particularly, I'd like for you to take away this evening something quite important, which is that quantum technologies and quantum computing are not just the latest fad. They're not, just the next Intel processor, the next generation. Rather, there's something quite profound about the way that we would like to control nature and make it do certain things that are useful, like computing or like communicating. So let me step you through that from a certain angle, and hopefully by the end of the lecture, you'll understand what is different about quantum technologies. So let's start with situating where this new field of research is. Quantum information is what I would call it. And it's really at the interface between multiple disciplines, which is always a fertile ground. Physics, computer science, very importantly, the study of information, mathematics, and philosophy. And this is really where the work happens. And there are people who live in different departments doing the kind of research that I do. Let's start with philosophy a little bit. Let's take a step back and go all the way back, in fact, to several centuries BC, to the Greeks, and with this very telling conversation that Democritus wrote between the intellect and the senses. And I'm not going to read off my slides very often, but here I'll read this off. The intellect begins by saying that by convention there is sweetness, there is bitterness, and there is color, but in reality only atoms and the void. Now, for a physicist like myself, this already puts Democritus shoulder to shoulder with any philosopher until the Renaissance. Now, the next thing is really the big one, and the senses reply, foolish intellect, do you seek to overthrow us? Well, it is from us that you take your evidence. And this throws Democritus right smack in the heart of the 20th century. This is epistemology, the theory of knowledge. And quantum mechanics, quantum theory, is really a theory about knowledge, about our ability to obtain knowledge from the universe. You could almost call it quantitative epistemology. So Democritus came up with something else, which was very important for us modern physicists. And this was this idea that matter in general was not continuous. You couldn't take a piece of apple and keep chopping it up. And nowadays it's fairly intuitive that eventually you fall upon atoms, which are these discrete units of matter. And if you break that down further, you no longer have, an element like gold, you have something else. That's the basis of nuclear physics. But for a long time, it wasn't obvious to people. And the important concept here that links into quantum theory is this aspect of discreteness. And in particular, when it comes to information, to bits, that I would like to say that the universe as a whole, in fact, if you think of information, comes in discrete packets of information. And that indeed that information is discrete, and moreover, that if you look at the universe as a whole, you might argue that in fact there is finite information contained within the universe, which defines a maximum amount of information you can obtain from any given measurement, some fundamental limit. And in fact, there is a scale to that. I'm not just talking randomly. There is something we call as physicists a fundamental constant, which relates exactly what I just said. And that fundamental constant is Planck's constant. It relates how energy, this comes in discrete packets, but moreover, and I'll convince you of that this evening, I hope, it discretizes information fundamentally at the universal scale. So I could go on to give you the introduction, which the historical introduction has been done that way, which is to tell you, which would have been to tell you about waves and about Niels Bohr and about Erwin Schrödinger and how you have to complete the circle around an orbit. I will not do that this evening. And I could tell you about Schrödinger's cat and the paradox and being alive and dead at the same time. But this is way overplayed, and I don't think it illuminates much. So I will also not tell you about that. What I will tell you about, however, is probability theory. Why? Because all of science really is built on probability theory, because the observation of a single event does not tell you much. It only tells you something is not impossible. So really any observation built over time, any model built over time will leverage probability theory in terms of making a statement. If I do something, what is the probability that something else happened, cause and effect? And so I can represent, for example, a coin toss between heads and tail as, you know, if it's a fair coin, I have the probability of heads as being 50% and the probability of tails as being 50%. So far, so good, not too complicated. And this is all great. This is all what we would describe as classical probability theory. And at this point, nobody in their right mind would say, well, before I measured this coin to be heads and tail, it existed in some weird superposition between head and tail, and you know, there's a parallel universe in which it was head and another in which it was tail. This is not the right description. But I could also describe the state legitimately of this coin while before I make the measurement as its state before measurement, which is 50% heads and 50% tail. This would be just some description of the system before I measure it. That's all fine. Now, I'm going to jump ahead, and then it hopefully will all make sense once I bring it together. This was probability theory, very basic. Now, here is another concept: complex numbers. Now, some of you might be shuffling in your seats. Maybe you haven't even seen it or something, but it's actually quite simple. You take the real numbers, the ones you're familiar with, right? 0, 1, in fact, 1.1 or 0.1. Add to that the negative numbers, right? They range from 0 towards the negative out to minus infinity, and all is well so far, right? This is a one dimension. Now, let me add another dimension to this, which in mathematics speak, we call that the imaginary axis. Though really, I think that's just hiding the point away. It's not imaginary, it's very real in a sense that we can use it. We can use it as a concept. And so let me show you exactly how we use that. We label that secondary axis with something which does not exist on the real axis, simply because I've defined this single axis to be real. I need something which isn't on the real axis, and so we decided to call it imaginary. But this thing is the square root of -1. The square root of -1 is interesting because indeed it doesn't live on the real axis, but it has one more property which is very interesting, and which we'll get to in a second. You can label now in this two-dimensional plane a two-dimensional number, essentially, which is called a complex number. And it has a certain amount of 1 here, a amount of 1, and b amount of the square root of -1. Now, what you will know about square roots of numbers is that if you multiply them with themselves, it just gives you what is inside the square root. So the square root of -1 multiplied with itself is just -1. So that's quite neat, because if I now multiply this complex number by the square root of -1, I end up just on the other side of this plane here, in another quadrant. And because I've multiplied simply square root of -1 by 1 and square root of -1 by itself to get -1. And now I have a certain amount of -1. And I can keep going with this. And what you'll notice is that it just rotates, right? It just rotates around the plane. And in fact, complex numbers, if you're going to be very simple about it, complex numbers are rotations. This is really what they do. They're one-to-one with rotations, and they're one-to-one also with waves, right? So complex numbers embody waves. Now you're thinking, ooh, now I'm getting something. Quantum, I've heard about quantum being something about waves, and here Dorian's telling me about complex numbers and waves. Well, you are absolutely right. It's a great moment when you can tell your audience whatever you're thinking, you're absolutely right. Complex numbers and waves are very useful for quantum theory because of that, and we'll get to that in a minute. So a mathematician, could have come along about a century ago, early 20th century, when probability theory was being developed, complex numbers, the late 19th century. A mathematician could have legitimately asked the question, well, what if we invented a probability theory that used complex numbers? However, no mathematician asked that question at the time. Instead, the physicist came along. Yeah, it's called quantum mechanics. So that is quantum mechanics, a complex probability theory, right? So what do I mean? I mean that before a measurement is performed on a quantum system, before I look at whether my quantum coin now is heads or tail, I represent the probability. We'll get to that. There's a subtlety, but we'll get to that. Well, I represent the prefactor here, the state of the system, with a complex number, an independent complex number for heads and for tail. Now, you might be wondering, well, what does that mean to have complex numbers as prefactors what does it mean for measurement? Well, it doesn't change. This is the important bit. This is the key bit. It actually does not change what you measure in the end. What you measure is still going to be heads or tail. There's only two options in my quantum coin, is that it's heads or tail, and that the sum of heads and tail, if I take this, it's called complex. If you don't understand that bit, don't worry about it. But you just need to manipulate that complex number to give you, again, a real number, and it's called a complex modulus. And then the sum of those need to be equal to 1. That's just how it works out mathematically. But ultimately, you've represented the system before you've measured it with complex numbers. And that simple map right here is the postulates of quantum theory, that everything in the universe follows these rules. Whatever state you can identify that you measure, before you measure them, it's represented by some complex number, right? Now, I will add one thing to the postulates of quantum theory, and that is Schrödinger's equation. Schrödinger's equation, if I manage to give you, to a broad audience, introduce you to Schrödinger's equation, that's great success. Now, Schrödinger's equation, you don't need to understand math. I'm going to walk you through this, don't worry. It says that this state of my coin here is affected by something called the Hamiltonian, which is just the energy of the different states in the system. And the energy of the system applied to my state basically gives me the evolution of my state, of these probabilities. That's all it is. That's Schrödinger's equation, right? The evolution over time of probabilities is just given to you by energy. That's it, right? So this is very powerful. Now, okay, that's one thing. The second thing I'd like to mention is that you go now from something which, when you have before you make a measurement, you formerly had some very simple probabilities, 50% heads, 50% tails. But now I have complex numbers that describe the outcome of measurements before I make a measurement, right? And it turns out that when you have two complex numbers, that is sufficient to represent something on a sphere. So you have enough parameters out of two complex numbers to represent your state before a measurement on a sphere. Now, this is where quantum mechanics starts to talk about superposition and the ability to have waves in the system, because this surface and the change over time of some state on this surface can be is like a wave. It is essentially embodies a wave. And if I represent my state by an arrow, which say points along the equator here on this three-dimensional surface, that is some kind of superposition between heads and tail. Now remember, I don't get to see that superposition. This is the way that we visualize quantum information before a measurement. When we make a measurement, we only ever get heads or tail. This is the strangeness of quantum mechanics, right? So you might think, well, what do you mean? I mean, is this just a figment of our imagination? Is the wave function real? Well, my reply to that is a very good question. We don't know that, but what we do know is that quantum theory predicts exactly the outcome of measurements, and that a normal probability theory would not. And we represent information on this sphere. Now, here's another important concept that is key to quantum technologies, and I'm trying to bridge that now, which is you cannot copy, right, quantum information. So what is required in a copying operation? If you want to take one bit from your computer and copy it, you need to measure it. You need to look at it and then replicate it in another bit. That would be to copy. But me making a measurement on this quantum system collapses the system. This is where the idea of wave function collapse comes in, is that whatever the state is before the measurement, it will only ever show me heads or tail. It collapses that superposition into one or the other. It's a probability of outcome. And so from that perspective, I cannot simply measure my quantum state and copy it. There is no operation in the universe that allows me to copy this quantum state here. This is called the no cloning theorem of quantum theory. And if you're sort of thinking about cryptography and secure communication, well, this is the basis of it. There cannot be an eavesdropper which copies quantum information. And that is proofed and secured by the laws of quantum mechanics, the laws of physics. All right. So yes, computer scientists. So we talked about computer science, and you know, we haven't introduced the full picture for those who are more computer science inclined. Let me make a slight modification to this picture for our computer science friends. Now it's better. Now I'm being a bit harsh on the computer scientists. In fact, I think the greatest discoveries in physics in the 21st century will come from a computer science perspective on physics, from the perspective of quantum information. That is really that would be my bet. Now, what I've been showing you as this sphere, this representation of essentially a two-level system, heads or tail, true or false, on or off, etc., 0 or 1. These are all logical states that are equivalent. This sphere is the qubit, the quantum bit, right? And this is what I'm going to use from here on in describing what happens next. Okay, so now I do want to take one step back before I dive into some more quantum technological things, which is that our current understanding of the universe is really that it all boils down, as I said, to discreteness of information. That you can, and there is no simpler bit of quantum information than the quantum bit. So everything is about quantum bits. You can break down the entirety of the universe as a set of quantum bits. And in fact, it's even more powerful than that, is most modern quantum computer scientists and most people working on quantum physics nowadays would agree with the picture that quantum theory is not just a physical theory. Quantum theory is not physics. Quantum theory is the operating system on which we run physics, right? It is the thing that we port electromagnetism onto. The electromagnetism is the app, and it needs to run with quantum theory. The strong nuclear force, nuclear physics, needs to run on the operating system of quantum information. The weak nuclear force is the same. Gravity, even though we're still working on that arrow, to be fair, I acknowledge that, but most physicists will agree that quantum gravity is the inevitable description of gravity in our universe because of this concept of finite information. And so we even have a term for it. It already exists in the English language. That process of porting this physics onto the operating system is called to quantize. You quantize your phenomenon in order to make it agree with this complex probability theory. Right, so why do we not see quantum on a daily basis then if it describes everything? Why is it that the quantum operating system is so elusive? Well, because we live in a world with trillions and trillions and trillions of quantum bits, right? So my everything around us is the air, everything is trillions and trillions of quantum bits that average out where we don't get to keep track of the measurements being made, and it averages out into blobs that we'll call classical blobs, right? And that's why we don't see this discreteness. It's just an averaging out. It's because Planck's constant is tiny, actually, right? It's the scale of discreteness is tiny, and that's why we don't see it. But so if we do want to see it, we need to go to the extremes. We need to go to ultra cold temperatures, or to tiny, the atomic scale, right? The single electrons, or we need to go to ultra fast, ultra high energy physics, like what happens at the LHC. This is how we probe the discreteness. This is how we probe Planck's constant. Right, so I could move on to tell you about the uncertainty principle, right, which is a bit the title of my talk. I do want to get to that. And I could tell you about, De Broglie and fundamental physics from the early 20th century, but I think you've gotten at this point that I don't want to go the historical route. I want to go the 21st century way into quantum theory. And indeed, Heisenberg very famously introduced his uncertainty principle to do with position and momentum. What I will keep from Heisenberg is not that. Again, I'll come back to our qubit, our basic unit of quantum information. But what I do want to say about Heisenberg is this quote, which is beautiful, and I'll come back to it, which is, what we observe is not nature itself, but nature exposed to our method of questioning. Wow, that's powerful. That's the stuff of quantum mechanics, right? This is how measurement impacts what you see, right? How you question nature is important. The context is important, right? So in the qubit world, coming back to this sphere, what is then the uncertainty principle? It still applies. There is still something fundamental about the uncertainty principle in the qubit world, and this is how you write it down. It's got three axes, X, Y, and Z, and it's got Planck's constant, because that sets the scale of the uncertainty. It sets the scale of discreteness. So I will get to how we derive this, but first, I want to remind you of the rules of the quantum game, which is that this state of my system, before I do any measurement, is described by this wave function and by complex numbers. And again, whenever I measure, I have a probability of getting one that is given to me by the coefficient in front of one, representing where it is on this sphere. And in the end, the sum of all measurements need to sum up to one, right? I mean, this is still normal probability theory in the sense of measurement. Now, what if my state points in the X direction before I make a measurement here, right? So I mentioned this already earlier. In that case, if I make a measurement whose answer, so what I ask from the system is my system 1 or is it 0? That is, I'm making a measurement along this, what I would call the Z-axis. Is it 1 or is it 0? In this case, it's not a very well-defined question because my state is not pointing along 1 or 0, it's pointing in some other direction. And so in that sense, I get 50% chance of getting 1 and 50% chance of getting 0. And that's because I didn't really ask the right question. But what I could have done is I could have used my Schrödinger equation. And this has to do a little bit with control, how you introduce the idea of controlling quantum state. You do it via the Schrödinger equation. Schrödinger gives you that. And what I can do with my Schrödinger equation is to rotate this state on this sphere. I can rotate it from pointing in a superposition, which was not a well-defined answer to my question of, is it pointing up or down? I can make it point in a direction where the answer is well-defined, where the answer is always, when I make a measurement, 1. So you might have heard something about quantum mechanics being probabilistic. It is only probabilistic if you don't ask the right question, if you haven't done the right operation before measurement. Determinism is possible from quantum theory. The way you achieve it is that you prepare your state along the right axis before you make a measurement. And then I always get the same answer. In this case, I always get 1. So I can go from a superposition to something that is well-defined before making a measurement and always get the same answer at the output. This I can do locally by controlling the system locally. Okay, so now how do we get back to the uncertainty principle? Well, this is the key. The uncertainty principle tells you that if you're trying to learn about your system along the axes where your state is not pointing, then you will inevitably end up with some randomness, with some distribution. So if I'm trying to learn about, for example, X and Y simultaneously, here Y, my state is pointing along X, which means that it has a very poorly defined distribution along Y. So if I were to try to make a measurement that is consistent with, is it pointing along plus Y or is it pointing along minus Y? Then I would not have a well-defined answer. It'd be, well, it's 50-50. But if I asked how it is along X, then I would get a well-defined answer. But there's a fundamental trade-off between the uncertainty in these measurements, in repeated measurements. And I emphasize this, you need to re-prepare the state and measure it over and over again. The uncertainty principle is something about statistics, right? About the uncertainty on certain variables. And here, X, Y, and Z are not compatible observables of my qubit, right? Because they're along different axes. So this is it. This is what the uncertainty principle is. And it comes from the fundamental way that quantum information is built as a represented on a surface before a measurement is made. And again, everything is qubits. All right, so just at this point, you're probably thinking, okay, maybe I'm starting to get this quantum stuff. This is good. But we're here. We're at this we're approaching this first little bump, and I'm sorry to say that we're not quite yet at the summit. We've just passed, and we're seeing the actual summit. This was a false summit. We're getting to the meat of stuff, and this is quantum entanglement, right? And this is where, if you thought this was weird so far, quantum entanglement is really weird. All right, so let's have 2 qubits now, right? And I promise it is weird, but I'm gonna step you through it. So let's take our first qubit. Our first qubit is going to be, again, in a superposition. That is, this qubit on the left, I could rotate it with my Schrödinger equation to be always in 1 and make a measurement, and it would be always in 1. But here I decide to put it in a superposition of 1 and 0. And then I'll take a second qubit, and I'll prepare that qubit in state 1. So that every time I make a measurement, it's always 1. And I will bring these states together. Now, this is just an artifice of notation, but it's useful. But it's just, I haven't changed anything. All I've said is I've combined my possible states of the system into one combined state, right? So the first state being 1 or 0, right? And the second state being the other one, right? This should actually be a 1. I'm sorry, this should be 1, 1, and 0. So I need to correct this on my slide. But anyway, the point remains. You just have one qubit in superposition and the other not, right? Okay, and then I make these qubits interact. Now, here's the key feature that you need to understand. In order to create entanglement, you need interactions. Why? Because interactions is what embodies conditioned logic on an other qubit. So this is how, for example, I could produce some rotation, some change in my second qubit state as a function of what the state of my first qubit is. So you might think that's a little obtuse, but actually all of interactions are conditional operations, because if there wasn't conditioning, then you couldn't talk of an interaction, right? Interaction is if I do something, you do something else, and we it's like a dance. So you need some conditioning in interaction to make sense of it, and this is precisely what we represent here in terms of bits of logical operation, and here with quantum bits is the same thing. So we just have a conditional operation on the second qubit based on the first qubit, and these interactions can happen any way you like. We've broken them down in terms of fundamental forces as physicists, in terms of electromagnetism or nuclear force or gravity. But every interaction in the world in the end can be boiled down to these things. And this is what gives you conditional logic. So what does that do to our quantum state if I do a conditional rotation? Well, it changes the first bit in this state. That's it. You end up with, instead of you flip your second qubit conditioned on your first qubit. And that's how you get your new quantum state. Now, this quantum state is very interesting. It's very different from what we've encountered so far. And let me show you how exactly, right? So this is an entangled state. And the way that it's different is that, first of all, now I can take these qubits and separate them. This is quite an important thing here. I can separate my qubits in space while preserving this description. I haven't done anything else to my qubit but to separate them in space, right? And I can no longer separate. You'll remember this operation where I said it's just an artifice of notation to bring them together. Well, now I cannot separate those anymore. They're no longer separable states. So what does that mean? Well, remember how I could locally have an operation that would give you a deterministic answer, right? Locally, I took my qubit first, and this little qubit, I was able to prepare it in, say, state 1 and always get 1. But now I've made that qubit interact with another qubit, and I've sent that second qubit way out there. It could be at the other end of the universe. Here's the key. I am now no longer able, whatever I do, to get a deterministic answer out. Right? I'm going to pause for effect because this is the key bit here. I was able to get determinism, but as a result of this interaction, as a result of this entanglement, which, independent of how far I throw that second qubit out, I am no longer able to use my Schrödinger equation to get a deterministic output. Instead, I get pure randomness. Unless I know what happened to that second qubit, I will always get pure randomness out of a measurement in my first qubit. So this is the crux of entanglement. And yeah, so this is precisely the operation that I was representing, that you're no longer able to rotate that to get that superposition to get deterministic output, right? And this precise link that remains between two qubits, the impossibility to get a deterministic answer, is what Einstein called spooky action at a distance, because what it represents is that the unknowability of these states is extended across space, that we're no longer able to get what physicists, until quantum mechanics came along, physicists thought that reality was defined by local measurements. You could learn everything you needed to know about reality by making local measurements, so-called local realism. And now this very thing I just described, entanglement, means that you're no longer able to do that. You cannot describe the state of the system locally anymore. You need information from, it could be the other end of the universe that you could need more information from to define the system locally. Right, spooky action at a distance. Now, you don't just get spooky action at a distance with quantum entanglement, you can get Nobel Prizes as well. And this is precisely what the three gentlemen got last year in 2022 for experiments with entangled photons. So in this case, two qubits, which are photons, which were entangled and sent apart, and which established the violation of Bell inequalities, which is precisely this bound on knowledge that you can get from entanglement. and pioneering indeed quantum information science, which was my field of research. Right, so with the bit of time that I have left, I want now to connect these foundations to technology, to this very, very interesting field of technology that is now progressing. And one thing that you might read in the news, there's always some flashy stuff with quantum. You can often get confused, as you can imagine, with exactly how these things work, and there's a lot of people willing to exaggerate certain things. So, for example, there's something called, legitimately, which physicists will use, called quantum teleportation. Now, it's not Star Trek, sorry to say, and sorry to disappoint people in the audience. We're not going to be teleporting Spock anytime soon, but what we will be able to do, and what we are able to do, is to teleport quantum states, right? What do I mean by that? Well, if say I have a transmitting station here, and I have a receiving station B, and I have some state here, some quantum state. Again, remember the no cloning theorem, right? I'm not able to copy quantum information. This is the important bit with quantum teleportation. So I have this quantum state which I want to send to the other end of the universe, for example, and it's represented by these complex numbers. What I can do is I can use an entangled photon pair, for example, an entangled pair of quantum bits in what is called, in honor of John Bell, a Bell state, and I can split these qubits to very, very far distances. Again, entanglement persists over arbitrary distances, as far as we know, and I can then perform an operation here between my entangled photon A and my qubit, which I don't want to measure. I don't want to collapse it. I want for it to stay exactly as it is. I can now do an entangling operation between my qubit that I want to send and this Bell state. And what will happen upon now sending the results of this operation, so there's still classical information being sent. This is the key. There's no instantaneous transfer of information. I will send the results of that measurement here to my receiving station, but all of a sudden the magic is that the state C will just pop out the other end. At no point did I have to measure my quantum state, and yet it'll just pop out at the other end after sending a couple of bits of classical information to the receiving station. This is quantum teleportation. Now, is it useful? Well, I don't know, but it's very cool. What it might be useful for is quantum computing remotely, right? So if you want to have quantum processing units which are delocalized, you might want to teleport some quantum states from here to there without having to carry your physical qubit across the row. And so teleportation can be very useful for that, right? But who knows? Perhaps we'll dream up of something else to do with being able to transport quantum states without having to measure them. Okay. Now, something else which I alluded to earlier is cryptography, right? The fact that you cannot perturb a quantum system without collapsing it is a key to protecting information, because as soon as you have, for example, say you have Alice and Bob, who are typical parties who want to exchange information, and they want to exchange something securely. You always have Eve, the eavesdropper, and the way to, of course, eavesdrop is to funnel out a little bit of information from a channel and to measure it, right? So you fundamentally measure information in order to find out something. That very act of measurement perturbs the quantum channel, and you can detect that through the violation of Bell's inequalities. That is, if you have perfect entanglement, which violates Bell's inequalities, it's a bit of a technical term, but all you need to know is there's a certain criterion past which you know that you have a maximally entangled system. And under a maximally entangled system, there is no way anybody could have eavesdropped, because it would have lowered that entanglement. And so in that sense, it's protected. So you can do tests which verify by the laws of physics that you have a secure channel, right? And this was posited using the entanglement scheme by Arthur Eckert in Oxford 3 decades ago, and verified by an Oxford team very recently, which is a nice link for for Oxford, but moreover, by two fellows at Balliol here who are involved in this work here in 2022, Raghu, who was your host, and David Lucas as well. So a very nice connection with quantum information theory here at Balliol in Oxford. Okay, quantum computing now. I'll try to get across some of the taste, the flavor, but I won't be able to give you a full picture, obviously. Everything in computing is about operations, logical operations, right? Between zeros and ones. I think that's a familiar way to introduce computation. You have logical gates, and again, interactions in nature. If you want to represent interactions in general, it's logical gates, as I mentioned. So really, everything is about logical gates between registers of bits. It's just how you represent it. So great. Now, what about quantum? Well, what makes ultimately systems, quantum systems, very hard to simulate for your PC, and in fact, every PC in the world, in fact, every PC put together in the world so far and into the future, is entanglement, is the fact that you have these interactions which cause conditional information to live across a system, and within a very, very large space of possibilities. And this property, entanglement, is what makes solving quantum systems hard. So let's flip that on its head and let's use instead entanglement. What if we used a system which leveraged entanglement, which used entanglement as a resource to crack those very problems which we said were difficult for a normal machine, right? Well, that's a quantum computer. I mean, you just need to represent now you need to break down your model, whatever system you're trying to crack, discretize it as a number of qubits, and then handle entanglement within that qubit system and port it back to an answer which you care about. This is the bottom line of quantum computing, and not the one who came up with it. It was an idea in the 1980s by Richard Feynman, really, to what makes quantum systems hard is entanglement. So let's use a quantum system to crack another quantum system. Now, this might be a little bit, restrictive in the sense that you think, well, okay, but there's only so many quantum systems I can care about. But interestingly, what we found is that there are certain problems which don't necessarily have a clear mapping to quantum systems. For example, prime number factorization. Now, you might think that's a little bit of a contrived example. You went from quantum system to prime numbers, but actually our entire banking security relies on the difficulty, the mathematical difficulty of factoring a very long number into its prime component. It's called prime factorization, and our banking security is based on a cryptographic code called RSA, for public key distribution, and it's based on the difficulty of cracking prime number factorization. Normal computers, impossible to do, on at least as far as we know. Quantum computers, this was proven, this is mathematically proven in the 90s, and this is why the whole field boomed after the 90s. Quantum computers can crack that exponentially faster. An exponential is a very fast rising number, right? And it means that something which could have taken millions of years for all computers on the planet to do could be done within the span of days or weeks, or it doesn't matter. Something tangible could be done with a quantum computer. And this is what worries, obviously, a lot of three-letter agencies across the world, and is fueling a lot of the research into quantum computing. But I want to spin that again back to the physicist's take, which is that the universe is quantum. If we want to understand the universe, we need a way to simulate the universe, and a quantum computer is the only way to simulate really quantum systems. Right, that's why there's a lot of companies working on this, like Google and IonQ and IBM. And with this very final minute, let me tell you about what I do. What I do is to try to build connected quantum systems. So precisely this operation of sending photons across distances and to leverage entanglement to do operations is what I try to develop using semiconductors. something called quantum dots, which are exquisite sources of single quantum bits, photonic quantum bits, which we can then exchange on a network. And these photonic quantum bits can be connected locally to a single electron quantum bit and have entanglement between that electron, those photons. And so we can build up what might be called a quantum internet eventually. So this is what I'm working towards. Right, with that, this closes my lecture, and I'm open for your questions.
Thanks a lot, Dorian, for that wonderful introduction to quantum technologies. So just a reminder again that if you have any questions, to type them in the Q&A button at the bottom. Maybe a question for me just to get things going. So you spoke about encoding information in quantum systems as qubits, but you're an experimentalist, I'm an experimentalist. What does that mean in practice? And especially going from encoding the information in trapped ions to solid state systems, what changes?
Yeah, that's a great question. It's really, again, about how you isolate your complex system, which might be an electron, a sea of nuclear spins, or a trapped ion in vacuum, and isolating that complex system into a qubit, first of all, right? So you want to be able to isolate, look at some two-level system, two quantum levels, and then once you have those two levels and you can control them, again, via Schrodinger's equation, then you can manipulate the state of that, on or off, 1 or 0, to be in any arbitrary superposition it could be using lasers, right, to do that Schrodinger equation operation, or it could be using microwaves or anything that interacts quantumly to some extent with a quantum system can be used to control a quantum system. And the name of the game is being able to produce any arbitrary state on this sphere, ultimately, having arbitrary control.
Okay, great, thank you. All right, so the questions are coming in now. So we have one from Radvis Pastoyu, sorry if I mispronounced it. So what semiconductor quantum dots are being investigated? 3 to 5 base, such as indium gallium arsenide, or colloidal quantum dots, such as lead S-based instead?
Right. Yeah. The colloidal quantum dots. All of the above, really. There are systems which are more promising than others. What do I mean by promising? Well, it comes down to the metrics. What is it that we want out of these light-emitting quantum systems? We want to be able to emit single photons and only one photon. We want that photon to be the same every time it comes out of the system, which is not a trivial thing. And we want the spin, the electron spin that then gets entangled with that photon, to be able to keep information for a really long time, sufficiently long that the photon can travel across the Earth, for example, and so we can untangle systems remotely. And the key bit here is that this electron now is in a very complex environment in semiconductors with a lot of other spins around, etc. So a lot of the engineering that goes into quantum dots is, well, how well can we isolate that little spin, that little qubit, from interacting with everything else? Because interaction is also what does measurement at the end of the day. So you need to isolate quantum systems from everybody else measuring them. I want to be in control. So the answer to your question is, we're exploring a whole range. At the minute, gallium arsenide quantum dots are a very promising avenue because they combine good spin properties and good optical properties.
All right, thanks, Dorian. So next question from Andy Watson. We're all familiar with coding and algorithm. What will programming look like in a quantum computer?
Yeah, it'll look relatively similar in a sense that, at the end user at some point may not even know that they're using a quantum processing unit. This is the dream, right? Where you submit a task, and that task could be broken down into things that are easy for a normal computer, and the core bits of your routine, which might be hard. And then that core bit of the routine might be sent to some cloud-based quantum processing unit, or if you're really rich and really lucky in the next century, you might have access to a local one. But then that gets broken down into, of course, the physical hardware implementation. So you need some kind of way to break down your routine in terms of an algorithm, a known algorithm on your quantum computer, and then a set of gates. So this is the role of the compiler. And there's a range of activities on certainly doing exactly that. It's non-trivial, as you can expect. I mean, it depends exactly really in the details of the architecture. What is the connectivity of your quantum processing unit? What is its resilience to error? Will matter a lot in terms of how many gates you can perform. What is the optimal sequence, right? So there's a lot that goes into it, but ultimately it's the role of some kind of compiler.
Thanks, Dorian. So next question from Ben. So quantum theory and domain seem so universal. Could you explain what a non-quantum entity is and how it can be recognized?
So I think it boils down essentially to entanglement, right? So, and the way I described entanglement, which is this conditionality between distant objects, you cannot have that coming out of what is called the classical theory. So what do I mean by classical? It's something that, well, in this context of probability theory, would not use complex numbers to represent the system before you made a measurement, right? You could represent instead by probabilities exclusively by real numbers. But then you would be missing out on explaining some configurations of your apparatus when you're trying to do a measurement would be inconsistent, right? It would not, your real probability theory would not be able to explain what you're seeing. And so this, the idea of the day, it's about, a classical, the quantum state distinguishes itself by exactly what I mentioned, by satisfying the postulates of quantum theory. Obviously, that's natural. A classical state, and as I mentioned, it tends to arise once you average out this quantum behavior. So once you randomly sum a whole bunch of qubits, what you end up with is Newton's mechanics. Is that when you throw a ball, it will go into one trajectory and follow that trajectory classically. And this is the averaging out of that, essentially of the uncertainty principle, right, over time.
Thank you. So we have one question here from Laura Findley. What do you think the main uses for quantum computing will be in the future, and how long do you think it will take to get to them?
That's a very good question. I mean, I'm not personally interested in prime number factorization, though other agencies might be. And it's certainly not near term, because this kind of usage would require an enormous machine that is fault tolerant, et cetera, for really large number factorization. So I think that's some way up, which is good for the banking industry. The near-term applications, I think, will come in through more fundamental physics. I think that this is where these controllable, what is ultimately a controllable large quantum system that you can arbitrarily tune, can give you the ability to encode certain phases of matter, for example, non-trivial phases of matter that might not exist in nature, but you might want to explore, and give an answer to physicists as to how these arise. Topology, in quantum mechanics, etc., or quantum chaos. There's many subjects which are quite fundamental, and where a controllable quantum machine could give answers. Now, this would be the really near term, and in fact, currently, that's what physicists do in the lab in using these large quantum systems. A slightly closer one could be to use for very restricted tasks. For example, variational quantum eigensolving, which has to do with finding the ground state of a molecule. Maybe near-term machines which are sufficiently large could give a boost in some conditions to searching for the ground state of some complex quantum system. But these are really active areas of research, and a lot of people are betting on these sort of NISQ devices, noisy intermediate scale quantum systems, to give a small boost to certain tasks which are very difficult for classical computers. So this would be my sort of sequence of gains that we could make. The long run is, well, yeah, we might be able to run Shor, the quantum Fourier transform, and we might be able to run Grover's search algorithm, but these will take really big machines to do.
If I can maybe just follow up to that question to put you on the spot a little bit. So there are many different platforms that people are working on. So, ion, superconducting qubits, quantum dots, of course. If you had to pick one, which one would it be?
So for the NISQ applications, for the first physicists currently working on many body systems and trying to crack some exotic Hamiltonian, I think that the best platforms right now are superconducting qubits, trapped ions, neutral atoms, those which are very easy to control, but perhaps a little bit harder to scale to very, very large numbers. And this is where I think the transition at some point will happen. I mean, I work on systems which essentially bet on photons. Why? Because photons are very cheap to produce. A quantum dot can produce 1 billion photons in a second, right? Now, this might be a bit of an artifice, but at the end of the day, I don't need necessarily to have a physical footprint of my million qubit quantum computer in a very cold place. If I have something that literally spits out qubits one by one very, very fast, then I can use that light in what's called an interferometer. At the end of the day, there is some operations to do downstream, but you can generate on demand your qubits, and then they get measured, they disappear. These are photons, they disappear once you measure them. But this would be the architecture that I think could give really a boon, longer run, but not, it's a very difficult engineering challenge from a perspective of making these photon sources really spit out these qubits, like I say. So that's my bet. But of course, I'm very keen on all platforms. I think they're all there's a lot of promise in all of them. This is what makes it challenging in the field, because everybody's arguing for their own platform, and there's no really clear winner, and it's a bit contextual. What is it that you're trying to do?
Yep. Thank you. So we have a question from Stephen Freilich. Quantum dots have surface states that differ from the bulk electronic properties. How important would this be in the design of systems?
Yeah, it's true. So we try to stay away from surfaces. Is my bottom bottom line, especially for the optically active systems. So we bury these quantum dots. My picture didn't give that justice, but we bury these quantum dots in about 100 nanometers of a buffer layer before you hit any kind of surface. And indeed, there's a lot of surface fluctuation states which could indeed couple to both the spin or an electric dipole moment, which is what the exciton is, which emits light. And so there's a lot of noise that comes from surfaces, but we tend to go away from that.
Okay. So we have a question from Richard Wyman. Why can't Eve impersonate Bob and thus receive the message?
Well, Bob would know that he didn't receive a photon. I mean, I cannot exclude human error in the system, but I can tell you that if Bob is expecting a photon and he doesn't receive one, then he knows nothing's happened, and so he cannot build up a key, right? And so that's a little bit this fundamental thing, that Eve cannot just grab a photon, copy it, keep her copy to measure it, and then fake it to Bob, right? That's well, okay. Fundamentally, you cannot clone, right? And one even better way of doing this is entanglement based, because there what we end up with is testing a fundamental property, that maximal entanglement results from these Bell pairs being received by Alice and Bob. But ultimately, it comes down to the no cloning theorem.
Right. Thank you. So we have a question from Robin Paynham. When you talked about quantum teleportation, you showed the input to one qubit being an output of the other entangled one. How fast does this happen? And can information be sent in this way?
Okay. Well, information from the qubit itself cannot, right? If you actually want to send the full qubit, again, it's come back to the no cloning theorem, you cannot just measure the qubit in one shot and then send that information over. That can't happen. You would have to re-prepare your system many times, learn about it, and then send the classical information over. Now, perhaps if that's not what you want to do, that's fine. If what you want to do is send the qubit, really, if you want to send the qubit over, then what you need to do is entangle it first with 1/2 of a Bell pair. And then what that means is that you actually make your qubit interact with that half of the Bell pair, make a measurement, and actually collapse the wave function locally, which gives you an answer. It gives you 2 bits of information in one measurement. It's called a Bell measurement. And then you send those 2 bits of information classically at the speed of light, if you're using radio waves, that then is received at the receiver station. So this is the speed of light transmission. And then at the receiver station, what it does is simply modify the second half of the Bell pair according to the received measurements. And that identically reconstructs your initial qubit at the other end. So this is quantum teleportation. So it happens no faster than the speed of light, right? In order to really reconstruct the state at the other end, you need to send those classical bits of information, which can happen only as fast as the speed of light.
Thank you. Maybe another question for me while we wait for more from the audience. So you mentioned a few companies that are doing research in quantum computing, like IBM, Google. How has the involvement of these companies changed what research is being done in academia, universities such as groups such as yourselves, and what research is being done in the companies?
It's a blurry interface in the sense that there's a continuum between the two, really. But doing some kind of broad categorization, I would say that companies will end up picking one particular approach, obviously, which is the nature of companies, pick a particular approach that looks very promising and try to engineer the hell out of it to see if it actually works. And that requires settling on some of the design basics and not deviating from it, right? What academic groups are good at is questioning the assumptions and constantly, shifting directions and trying to, if we change this, does it work? If we change that, does it work? So this is where it's the same dichotomy that you would do in any field between academia and industry, I would venture to say, which is that academic groups are good for proof of concept, quick things at a small scale. So in other words, in the language of quantum computing, a few qubits to demonstrate that these things, you can do a conditional gate and you can entangle 2 things and you get Nobel Prizes and et cetera, et cetera. But at the end, if you need 1 million qubits, no academic lab is going to be able to do that. It just doesn't have the scale. So this is where companies then jump in and offer the scale of resources and the scale of quality control that is required to make things at scale, right? So this is their role. But again, there's a lot of very, very nice research happening in companies because, well, they have access to the largest quantum computing machines on the planet. And so physicists want to access them and do some really cool physics as well. So there's obviously an interface there.
Okay, thank you. I'm not seeing more questions from the audience, so I think maybe this is a good place to wrap up. Thanks again for your time, Dorian. Oh, sorry,
Thanks,
no,
Raghu.
we got
Thanks,
one few more questions coming in.
All right.
Maybe just a couple. So one from John Brooke. I'm an English literature student. How is all this going to change my life?
Very good question. I mean, at the end of the day, it's a bit like other big technologies, right? It's like AI, nuclear fusion, in the sense that we decide as a society that these are extremely important problems to crack, to understand. And so from that perspective, we collectively, including English literature students, have decided, right, that these are important. I mean, maybe not you personally, I don't know, but we have collectively decided that these are very interesting things that could change the world in a better way. So I think the involvement, the engagement is, well, do you think quantum computing is interesting after this talk or after other people's talk? Do you agree, right, with the way that we fund this kind of research? So I mean, this is the way that I think you could certainly engage. Now, will a quantum computer change your life anytime soon? It's very unlikely, because we will not. My bet would be we will not see something that an average that anybody in the street can plug into an iPhone and submit a task that actually goes to a quantum computer. I don't think that happens anytime soon. But yeah, I'm a bit pessimistic, but then again, I'm a physicist. I'm actually working on hardware, and obviously that biases my view of these things. And so no time soon will it affect you, I think, in a very direct way of actually tapping into the power of quantum computing. At the moment, yeah, it's more of a, where are we going as a society?
Maybe just one last question from Laura before we wrap up. And she asks, do you envisage that quantum computing will eventually become the norm, replacing classical computers, or will these be applicable only for specific applications? And I think maybe you've touched on this a little bit in your previous response.
Yeah, so I think it will definitely not. It will be a complement for certain types of tasks. So what quantum computers are very good at is when you have, and this comes from this kind of idea of measurement. Ultimately, you only get one answer, even though you have massive state spaces of these computers. You want to get a finite answer at the end, and that really is this kind of bottleneck. The art of building a quantum algorithm is to take many things and boil them down to one thing, right? What is the prime number factorization amongst all possibilities of this large number? And that's what quantum computers do. They're a many to one. So streaming video is a many to many task, right? Not a many to one. And so classical machines with gigahertz clock rates are very good at many to many tasks. So there will not be a replacement for that from quantum machines, I don't think.
Okay, I think maybe this is a good place to stop. So thanks again, Dorian, for your time, and thank you to the audience for your attention and all the questions. So this is the last online lecture for the year, but we'll be back again in January, and we'll see you then. Have a good evening, everyone.
Bye-bye, everyone.